Okay, perfect. Welcome again. Second lecture regarding bending. What we do is quick overview what we discussed last lecture, and then we're going to go a couple of examples, and then we go to asymmetrical bending. Okay, so focus on slides. So we said, okay, if we want to analyze a beam, there are basically two major theories: Euler, Bernoulli, and Timoshenko. And the difference is that in Euler beam theory, you basically assume that the planes remain plane and perpendicular to the neutral axis. And basically, in theory, it means you ignore all the shear effects in the bend beam. And Timoshenko basically incorporate the shear effects by saying, well, my planes, they no longer remain plane. So basically, they add a rotation to it. And then we did a quick example, like based on our so forget-me-nots. That's how I learned it. So determine deflection based on a force, and we compare it basically with deflections if we incorporate our what's that called? Our shear effects, and we derived a ratio which was they gave us a ratio of length over thickness, or we could basically say we could ignore it or not. But in this case, we said further is that during the bending lecture series, we're going to always assume that we have Euler Bernoulli. So the main sections, planes remain straight and perpendicular to the neutral plane. And we said that if we bend the beam, we basically will have a pure bending moment. And therefore, if you bend it, part of it will elongate, part of it will shorten. And then we said, well, we can see that as basically bending around the curvature with around the center of curvature at point C with the radius r. And then we derived by looking at an element before and after bending and different segments, and we derived what the stresses would be. And basically, at the end of the day, we said, okay, well, we can get an equation out of it that basically gives us a relationship between the direct stresses and our moment that we apply to it, our moment of inertia, and our location y, which is from the centroidal axis. And then we also do, in the lecture series, we also go into moment of inertia, but we covered that as a different topic, so we will not go into it. And that was basically, this is the equation we eventually end up with. Sigma z is equal to moments multiplied by y divided over ixx. And we said, well, okay, what if we have a moment not on the x-axis, but on the y-axis? We can repeat the whole procedure, and we could derive a different equation, which in this case would be m times x over moment of inertia applied y. And then if we have two moments acting on a body simultaneously, we said we can decouple that into a moment around x and a moment around y, and then we can basically superposition the stresses on that beam. So we get simply the direct stresses are equal to the moment around x over ixx multiplied by y plus the moment around y divided by iyy and multiplied by x. So before actually we go into this problem, let's do a different problem. I'll go to the whiteboard for this. And this problem is basically, we go back to our circle, we had a circular tube, and we're going to look at basically why in some cases the solution can differ based on your objective. So let's assume that we have a circular tube or fuselage, and we have an outer radius and an inner radius, and we have a thickness d. And then we have a center, so this is our inner, and we have a radius for the outer case. So from moment of inertia, we know that, well, first of all, we know that the stresses, if it's pure bending, is mx multiplied by y over ixx. So moment and the y location, those are basic standards, so we need to determine the moment of inertia. And we say that's equal to pi over 4 the inner inner radius can be written as the outer radius as well. So you get pi over 4 minus. So you can expand this. What we get is pi over 4 outer radius in this case, we assume thin wall. So this means t greater or equal to t squared is neglected. So that disappears. So what we get is, so in this case, these RO4s drop out, cancel each other out. This is t squared, t to the power 8, t to the power 4. So those all drop out. We get only minus becomes plus. So we get pi over 4 multiplied by 4 times r outer radius cubed multiplied by t. So we get pi outer radius cubed multiplied by t. So that's our moment of inertia. Furthermore, what do we know? Say, for example, we want to see if this fails at a given material. We want to always investigate the maximum stresses. So what do we know about maximum stresses? It occurs at y is equal to plus minus r. So when our y location from our central y is maximum, that equals basically to the radius. So if we plug that in, and there will be, of course, the outer radius. So if we plug it in, we get for sigma z equal to the moment. We plug in r0, it drops out with an r, so we get pi r outer radius squared t. So that will be our equation for maximum stresses. Now we can rewrite this to a couple of things. They assume that we have given a set of materials. So we have some freedom to choose our materials, and our materials are given as such. So we have some material properties. Let's go for steel, aluminum, titanium, and then we do a quasi-isotropic composite. And what we get is, we look at the ultimate strength of the material, sigma u, we look at the density, and we look at the price tag. And this is just material property, so this will all be given, so this is nothing that you have to be worried about. So I'm just going to write this up. This is parts per kilogram, this is kilograms per cubic meter, and this is megapascals, MPa. So, say we have given a moment, so the moment is known, we can rewrite this equation to determine the thickness. So we can determine, make another table based on, again, the four materials, say steel, aluminum, titanium, and a quasi-isotropic. By the way, quasi-isotropic means, like metals are isotropic materials, quasi-isotropic means that for a composite, there are equal number of fibers in the 0, 90, and 45 direction. Basically, it's evenly split in all directions. So you can make a quasi-isotropic material out of 0s, 90s, plus minus 45. But similarly, you can also make it out of plus minus 30 degrees, plus minus 75 degrees. That will be also quasi-isotropic. It has to do that if you determine for a composite, so we can sidetrack a bit. So the extensional matrix, the A matrix, becomes equivalent to an isotropic one. So if you would basically pull on it for that laminate, would have equal stiffness in the 1-2 direction. So that's a term isotropic, quasi-isotropic, sorry. So if you want to do the thickness, we can rewrite this. This will be then sigma ultimate for the given materials multiplied by pi r0 divided over the moment. Say if in this case, your radius will be given, your moment will be given, you know your ultimate, so you can determine the stress, the thickness required for each material. So you get 2.8. Add 2 here, 1.3. And then if you look at a different, say, parameter, say total weight, because that's also an important parameter, then we can say that the weight is equal, of course, to the volume multiplied by the density. So what we get is rho multiplied by A times L. A is 2 times the basically circumference multiplied by the length. So 2 pi r. So we get rho 2 pi r multiplied by L. So we can determine that ratio of weight over length ratio, that will be equal to 2 rho, and then let me see. Yeah, 2 rho, and then we can plug this in for there's a T here, by the way, for the thickness. So we get it's correct. See times thickness, so we get yeah. Okay. So if you do this, let me see what are my numbers. So the weight, we get 2.4. Oh, sorry, I looked at the wrong table. 6.4 here, 3.7, and 7.3. Then the weight will be 2.4, 2.0, 1.8, and 1.3. And then we can determine how much weight we have multiplied by the dollar, so we can get our equivalent price tag, 10.6, 13, 39.6, and then 2.29. So based on this, as an engineer, you have like a couple of options. If you're limited by thickness and you don't care about the weight and of the structure, then of course in this case your steel would be your best option. And in some cases steel is the best option. And again, if you're like actually determined or limited by thickness, you cannot exceed a certain ratio, then in this case the quasi-isotropic laminate will be the best option. And of course, again, if you want to have the lowest cost, then in this case, again, the steel might be the best option. So based on your parameters for the given same problem, you can have totally different solutions to it. And I will see in some of those, say, problems that you will see. Part of it is calculate, say, a given stress distribution or shear flow or direct stresses or torsional moments, and part of it may be, okay, determine what's the best solution to this problem. And then you might have given material properties, then you have to basically look at different ratios and determine what's the best problem or best solution to the problem. With that said, let's focus back again on the problem on the board. So last lecture, we basically ended on this slide. So you have given a problem. You have given a cross section of your beam at a certain angle. There's 30 degrees. And we are given a moment around the x-axis equal to, let me see, just equal to m or mx. Let's call this m for now. And then we have certain dimensions. Let's see. This is thickness. And the total length is A/2, so the total length is A. So you have to basically calculate where are the direct stresses and where does the maximum occur, where does the minimum occur. So in this case, what we have basically a beam that's no longer acting on the same axis system as our moment. So basically what we have to do is we have to determine what the moment is and how it will act on our structure. And the simplest solution in this case is basically decouple the moment into or looking at the moment, looking at the beam and a new coordinate system x dash and y dash, and decoupling the moment into those two coordinate systems. Similar to forces, we can just use moment, just decompose the moment as is. And what we get is that the moment around the x dash system is equal to the moment, applied moment, mx cosine theta minus, and the moment around the dashed y system is equal to minus m sine theta. We'll come to I will explain in the next slide why this actually minus and not positive. And you basically have to think about, say, you use the right hand rule. So in this case, moment coming out of the plane would be a positive, so you go in it, so it's negative. So that's a negative flight moment. But we'll talk about sign convention in, once before we start our asymmetrical bending. So in this case, what we know is that since we have now two moments around x dash and y dash, our stresses will be a superposition of those two moments. So mx dash ixx multiplied by y plus my dash iyy multiplied by x. So we know that moments are given, x and y coordinates are based on the cross section. So we have to determine ixx and iyy. So we can do that. There's nothing else than just a rectangle. So we can easily determine the moments or the moment of inertia. And yyy is basically the other way around. And then what we can do is we plug this in, so we get a sigma z. So we get 12, and then we get minus moment cosine theta over a cubed t y. This plus becomes minus 12 and sine theta. This is a to the power t cubed, and this is a cubed t multiplied by x. So this is our equation. Now we can basically plug in our values for x and y, and we have 4 coordinates that are of interest to us. Those are basically, let's call this 1, 2, 3, and 4. So we know at those locations either x or y are positive or maximum. So if we want to determine our maximum stresses, it will occur at one of those 4 locations. And we can know immediately that at 1, in our new coordinate system, both x and y are positive. At 2, x is positive, y is negative. 3 is y is negative, x is negative. And 4 is x is negative, y is positive. So, and based on our equation, we can already determine that this location where it's positive, this will become most negative. And at this location where both are most negative, so then these minuses become pluses, then our stress will become maximum. So again, why do we need both maximum and minimum stress? Because in some materials, the maximum stress and tensile compression is not the same. So you have to basically double check both. And we can rewrite this as a bit easier. Let me see. Let's take the 12 out and the minus out and the m. And then we can take a AT out. So we get AT here. And then what we get is cosine theta over t squared minus, no, this becomes a plus, multiplied by y, and then sine theta a squared multiplied by x. And our x and y locations, basically for location 1, sigma z. So location 1, that's equal to a over 2 plus t. So this is a over 2 comma t. Can you see this? Yeah. Actually, let's do it on the other side. It's a bit easier. So, equation 1. What do you say? Sigma z is equal to a over 2 comma t. Sigma z is a over 2 minus t. Sigma z at 3. Is equal is at location minus a over 2 minus t, and sigma location 4 is equal to, let's have this correctly here, minus a over 2 and then positive t. I can just basically plug this in. So let's plug this in. See, this is x is a over 2, so basically a drops and you get this is also t over 2, by the way, sorry. So for the first location, we get minus 12 and a t. Now we get what's that? Okay. Cosine theta, y is t over 2. So this 1t drops, so 2t plus sine theta, and then we get 2a. Yep. Minus 12m. Get all this. It's the same. So we could just plug in the location. So we get a over 2. So that's positive. So again, a over 2 and it's positive. So this is positive. X becomes negative. So this becomes a negative sign here. And then we get y is 2t. What do we have else? Negative, negative. So basically this all becomes negative. And then we get 2t, 2a. This is negative, positive. So this becomes negative. This is positive. So this is 2t, 2a. And then, as we said earlier, this will yield the most negative value. No, this yield the most positive value because of the negative moment applied to it, and this will yield the most negative value. And with that said, that would be it. And it's so another thing that I want to talk about this assignment or this simple problem is be comfortable by doing a lot of stuff by just variables instead of numerical values. I think in most of the assignments you will given numerical values, but I'd say 80 to 90% of the time it will be easy if you just start out using variables, simplify and then plug in the numerical values that you have given. Yes?
Intuitively speaking, if we look at a problem, can we identify the points where we'll do the maximum and minimum?
Yeah, you can, yeah. So in this case, we gave all 4, but you can argue like I did here by saying coordinate system, by saying by definition, by looking at the equation, what the form of the equation is, and by the form of the problem that you can know that you only basically have to evaluate point 1 and point 3, 1 and 3. That'll be sufficient. You don't have to do all 4. But if you're drawn, then it's on you. Yes?
So why did the moments that we replaced mx prime and y prime, why were they negative?
We'll get to that right now. So it has to do with sign convention, how the equations basically are derived. For that is, look at what's defined as a positive moment, what's defined as a negative moment. So going back to our lecture slides, so this was the assignment. So I think this is given in the book. I don't know exactly what page, but these are the definitions of your positive moments, positive shear forces, positive axial loads, torsion, and distributed loads, and all the derivations. So for the moments, how you determine what's basically positive and negative. Well, first of all, for a lot of things like the forces, it just goes by if the force pointing in the positive x direction is positive, it's pointing in the negative x direction is negative. Similarly for y and z. So for example, the p force, actual force is given in the positive z direction, so that's positive. Similar for the distributed load, if they're aligned with the positive direction of the axis, is positive. For torsion, basically in this case, the torsion T is nothing else than an in-plane moment. So that could be substituted by a moment around Z. It's basically the same. So for those three, we determine, let me see, is this given in the next slide? No. So those are determined based on if where yields a positive, where it yields tension in the positive quadrant of the two-axis system. So what that means is, let's look at mx, right? So if we look at mx, basically we create bending around y and z. So let's draw y and z axis. This is our shape. Let me quickly turn on the camera. So this is our shape. This will be our y-axis and our z-axis. And then we'll look at how the moment is applied. So what does it do basically? So based on this figure, if our moment, so this one is applied like this. So let's actually go for a square. So this is our cross section, and the moments are applied in this direction. So what will happen is that we deform like this, right? And now we look at the positive quadrants, or the 4 quadrants. So we extend our axis systems. We have quadrant 1, say 2, 3, and 4. And this is a positive, in this case, positive x, positive y, and positive z coordinate. This is positive y, negative z. This is negative y, negative z quadrant, and this is negative y, positive z quadrant, based on your axis system. So the coordinate systems here are defined by positive x and y. Here they are defined by positive y, negative z, because this is the origin. Right? So a moment is defined as positive when it basically yields a positive attention in the positive xy or yz or zx quadrant. So in this case, since this is attention, this will yield a positive tension. So in this quadrant, since the moment how we applied it yielded a positive tension in the first quadrant, that means that this definition of the moment is positive. So if you look at say a different case, again, let's look at my on the lecture slides. So we need to look at my. It basically moments around. It will twist around the x z axis. So again, we draw a cube, and yeah, so there will be the moment drawn like this. So this will be, so we deform, no, deform like that. We deform like this, right? Makes sense? And again, now in this case, this is our positive x, positive z quadrant. Again, we have tension here, so this is how the moments are defined as tension. So you have to always look at does my moment, how it's applied to my structure, yield tension in the positive quadrant. That's basically the theoretical way of how I look at it. You can cheat a bit by saying right-hand rule for mx and mz, and the opposite for my. That's how I have to remember it. Because if you look at it at the lecture slides, you would think, so mx here follows the right-hand rule by pointing your thumb in the x direction, in the positive x direction. Z follows the same rule, and my doesn't. Okay. And then if you look back on our example, the moment was applied in such a way that mx was basically in the opposite direction, so therefore we had a negative moment.
Okay.
So in most cases, when you come to problems, I often indicate if it's either negative or positive. And in most cases, these trivial problems will maybe cost you out of, say, 10, maybe a half to 1 point max on a problem. So it's not a big deal, but it's good to know why certain things are positive and certain things are negative. Okay. So with this said, we can look at basically asymmetrical bending. So up to now, we always assumed that our cross section had a plane of symmetry, but that's of course is not always the case. So let's go back. So what happens when our cross section is no longer symmetric? It's not longer a T section or an I section, but it's like potato shaped. So with that said, we basically do the same steps, but then, if you remember correctly, last time when we looked at the stresses, we said, okay, well, we have a simple radius or curvature for radius, center of curvature, and radius r, and then certain distance y above the neutral axis. So r here, and this is y. Now, this simple, so we didn't have any components of x. This is no longer valid. So if we look at it, say an element, we will have basically a component in x and y direction. So let's define the coordinates that we're going to work with. Simplify this a bit. Like this. We assume that we have a coordinate system given somewhere around the centroidal axis, x, y. And we started by saying that our neutral axis can be anywhere at the location. So this is our neutral axis. And if we look at a certain element, and basically we look at it, how the stresses will vary. So we call this psi. And of course, we again assume this also bends around the center of curvature with a given radius r. Or in this case, we assume that the radius is equal to rho. That's how Maxim defines it. So we can say that again, our stresses in z, in this case, are equal to psi over rho, and therefore our stresses in z equal to E psi over rho. And then we can also assume that we have a pure bending. This is important, so we have no actual forces. So if we take the integral of sigma z over dA over the cross section, this must be equal to 0 because we assume that we have a pure bending moment and no actual forces. So what does this mean? So we can plug this into it. So we get E over rho outside of it, since those are constants, and we can psi dA. So basically, this means that for this to be true, that our integral over the area of psi dA must be equal to 0. And this can be only true if basically this is only true if our neutral axis and centroid are the same. Centroid axis. This is also your first moment of inertia, by the way. So this is only true if basically our centroid here and our neutral axis coincide. So we can redraw our figure a bit. So what we know for this to be true, since we have a pure bending, that our neutral axis is coinciding with our centroidal axis. So we know that this is true now. And this simplifies our life a bit. So now this dimension is and the reason why it's drawn slightly different else it would simplify it, because it was simplified a bit. And we want to have the most generic case. So this is psi, and it basically goes to our centroidal axis. It doesn't have to be on the same plane, but it goes through it. So now we have to basically determine what psi is. We basically want to determine it, psi as a function of x and y. So let's define a couple of things. We're going to redraw this figure here a bit. And well, let's call this, we can basically assume the small point. So this is point A, and this is point D, this is B, and this is point C. And this point here, where basically x-axis and AC interact, that's point D. We also know, based on definitions, that corners for point A are, this is nothing more than x distance, and AD is the y distance. Okay, so we know that psi, which is AC, so psi is a length AC, which is equal to AB plus BC. We also know that this is known as alpha, so this angle between the centroidal axis and our neutral axis. So therefore, by the angle-angle theorem, this is alpha as well. So we can use basic simple geometry rules and simplifications to come up with the definition of psi as a function of x and y. So what we see is that psi is equal to AC, that's this length, that's equal to AB and BC. So we know that AB, you can use Pythagorean theorem, so it is equal to so AB is equal to AD multiplied by cosine alpha, and in this case AD is equal to y, so it's equal to y cosine alpha. Similarly, we know that BC, that's this section, is equal to EBE plus CE. And then we can use simple geometry rules again. We know that this is alpha, so we can define that BE is equal to ED sine alpha. So I use this triangle AB DBE, and we know that BC plus CE, in this case, equal to OE. O is the origin. Again, sine alpha. So we can plug these two together. So BC from these three, BC becomes ED plus OE sine alpha. And ED and OE is nothing else than x. So this becomes x sine alpha. So now we determined that if you plug this into this one, we know that psi is equal to x sine alpha plus y cosine alpha. And the reason why I shifted a bit also basically became, because it would coincide with center, then you could say psi is equal to x squared y squared. But this is the more generic case. And once we have basically brought this, so we know that what psi is, the same procedure follows as our symmetrical bending. So we can repeat that procedure. Basically, we can plug in psi into our stresses. So what we get is E over rho x sine alpha plus y cosine alpha. And then we're gonna say, okay, our applied moment must be equal to our moment due to the stresses, due to the integral of the stresses. So if we take the moment around x, that's equal to the integral over the area of sigma y multiplied by y dA. And similarly, moment around y is equal to the integral of the stresses. This is segment C still. X dA. So we can plug that in into both. And let's do for both separately. So what we get is, if we evaluate this integral must be equal to our applied moment, so we basically plug in sigma z into the integrals. So we get for mx is equal to E sine alpha over rho, and what we get is the integral a x y dA plus E rho cosine alpha integral of y squared dA. And if you remember the moment of inertia lecture, this is Ixy, this is Ixx. And we can repeat the same for the moments around y. The only thing that changes is here E E sine alpha rho. Now we get here is x squared dA plus E cos alpha rho, the integral over the area of xy dA. So again, this is Iyy, and this is xy. So we can rewrite it as a bit simpler or a more compact fashion. Let's use a matrix notation. So we get E over rho, Ixy, Ixx, Iyy, Ixy, and then we get sine alpha cosine alpha. So what I already did is I basically took these two equations. Notice that E over rho appears in all the terms, so I took that out of the equations and then rewrote it in the matrix format. So what we can do now is we always want our stresses on basically on left side and our moments as an input. So we want to take the inverse of this. So what we can say is that this is, let's call this matrix, let's call this A. Okay. So if you take the inverse of the matrix, basically means 1 over determinant of A. inverse, sorry. Yes, we take the inverse, so we get indeed ixx iyy minus ixy squared of y. And we get mx and y, and that will be equal to write a bit more compact, else not on the screen. X and y. This is equal to e over rho sine alpha cosine alpha. So we can now basically rewrite, use this definition of the stresses and substitute into this equation, because we can see basically that we have the only difference that we don't have an x and y, and we can get our final equation. I will write out this like before. So we get is sigma z and such not appear. This might be a typo in the lecture sheets. I'll double check that, but there should be no negative sign. Yeah, what we can get is then our final form, so my ixx I have to double check that's a negative sign there. Let me finish this though. Ixy squared is multiplied by x plus mx over y minus my ixy so we can get this as well, so you know what I did a bit more clearly. So we can rewrite this as so now you can see that we can substitute basically this part for the sigma stresses. And then we can say that the stresses as a function of our moments, moment inertia, x and y coordinates. I have to double check these two signs here. Let me go through it. Okay, yeah, this negative sign must be here. The reason is else the determinant, normally you do x squared, so basically multiply by -1. And the only reason why I think they do that, yeah, I know they multiply by -1. I have to double check again why you do that. It probably has to do with that you want to have a negative ixy here. because now if I have a symmetrical beam, say if you have any forms of symmetry, then we know by definition that Ixy is equal to 0. And let's assume that you only have a moment around, say, only a moment around x. Also assume my is equal to 0 and mx is not equal to 0. Then this equation reduces to our original equation of mx Ixx multiplied by y. So if it's any form of symmetry, moment of inertia is equal to 0 in Ixy. So this part drops, right? So if symmetric, this drops, this drops, this drops, this drops. Now we also said there's no moment around y, so now this drops as well. It's equal to 0, so this whole x term disappears. And here you can cancel out myy, so you get your original mx over Ixx multiplied by y. And that was the first equation that we derived. And therefore, I think the -1 comes to here. So basically now you have a uniform equation set. So this is your complex, most generic shape set of equations. And based on assumption of biology cross-section and applied loads, you can always reduce to your given symmetrical loading condition. Similarly, say let's assume that my is also not equal to 0, mx is not equal to 0, by the way, this is mx not equal to 0, but still symmetric, so Ixy is equal to 0. Then what we get is, again, this one is not equal to 0, so we get moment around y Ixx over Ixx Iyy x plus moments around x Iyy over Ixx Iyy y. So this cancels, of course, and this cancels, this moment of y cancels with this, and now you have your moments with due to combined bending moments. Yes?
Over there, I guess we shifted the matrix to the other side.
Yeah.
The inverse of that.
Yeah, if take the inverse.
So, inverse is adjoint over determinant, I guess.
1 over the determinant multiplied by the original matrix, right?
I guess you're so.
Hmm?
Should it not be Iyy to, I don't know, the term should be, I guess, switched. If you find out the determinant of that matrix.
So the determinant should be y squared minus Ixy, right?
Yeah.
There's a reason why we multiply by -1. So you basically still multiply by 1. You can always do this.
And that's how it does it.
Yeah, so then you get this correct form where you now can, if you have you remain consistent with your previous equations. So now you have your generic equation, you can always reduce to, based on simplifications due to loading condition and geometry. Yeah, I got confused as well, but that was stated as that. Let's see. I think this is a good way or good location to stop. So next lecture, so basically we discussed both symmetric bending and asymmetric bending, and that's basically the whole topic of bending. So the next lecture what we'll do is just do examples, okay? So we didn't have much time to do examples today in the previous lecture. And there are 2 examples given in the lecture slides. Let me see. Yeah, one of them, the equations are, the solution is given, and the other one is not given. And especially the first one, I can highly recommend you to do that at home as well, give it a try, because again, it becomes very good example of, so before we leave, I will actually show the problem. And I will just discuss it, and then in the next lecture we go and solve it. So let's go to the lecture slides. Yeah, sorry for that. So, yeah. So this is a very good example. It basically will test your mathematical skills, how comfortable are you with just multiplication of an equation and of a function. So what you have to do is you have given a moment around x. You've given the yield and tension and in compression. So that's the reason why you say sigma y c sigma y t is the yield, stress, and tension and compression. They're the same. You've given a value for a thickness t. And now you have to basically determine the value from the top flange when the moment when it doesn't fail. So it seems like there are a couple of things you have to be careful with. So for drive, so we have an I section, 3A, 2A, beta A, and everything is T. So it's symmetric. So you know that your, first of all, moment of x is given, so this is non-zero. You can assume moment in y, since not given, is equal to 0. This is symmetric, so your moment around x, y is equal to 0 as well. So your stresses reduce to this equation. Our first equation. We know that y is with respect to the centroid. But this value of beta A is unknown, so you have to find beta. So now your centroid is a function of beta. So in this case, what you have to do is you find your centroid. It's a function of beta. You find your moment of inertia, function of beta, because that's a function of y. And then you can basically, you have your yield is given, your moment is given, and there will be another trick there. You have to determine where is y. What is the value of y? Which will again be a function of beta. And then you can solve for beta. So what you will see that in this side, the left-hand side, this is given, this is given. These two will be a function of beta. So you can solve for what beta is. And it becomes basically a mathematical derivation process. And it's a good example because you have to be comfortable by doing this in these lectures. You will often have to do just reduce, take over to left-hand side, right-hand side, and come up, just work with variables instead of just numeric values. So we're going to focus on this example next week, and then focus on another example as well. Okay, thank you. Any questions, by the way? No? Okay.